Welcome to science class. Today, we are going to learn about galaxies. Galaxies are where virtually all of the normal matter sits. You'll find out what I mean by normal matter in the next video. We've talked about how space in our local area feels so empty. Even if you traveled at the speed of light, it would take you more than 4 years to get to the closest star. But on the insanely large scale of galaxies, those gaps look tiny. Here are some photographs of galaxies. They look like dense, busy objects. Bear in mind that these galaxies are tens to hundreds of thousands of light years across. Galaxies are collections of space dust and stars. Yes, there are more planets than stars, but remember, the sun makes up 99.85% of the mass of our solar system, so we should expect the galaxy to reflect that as well. So when we discuss galaxies, we say they are made of nebulae and stars, and that's basically it. But which came first, the stars or the galaxies? Let's get started. A galaxy is defined as a gravitationally bound system of stars, stellar remnants, dead stars, intergalactic gas and dust. Astronomers think that stars began forming before galaxies. Galaxies are extremely large, so it takes less time for individual stars to form than it does for a collection of objects tens or hundreds of thousands of light years across to collect together. Remember that the early universe was almost perfectly uniform in density. The closest large galaxy to Earth, Andromeda, is 2 million light years away. Between us and it is about as close as you can get to nothing. But many billions of years ago, the Milky Way and Andromeda galaxies would have been much less dense, to the point where you wouldn't really say they even exist. Over time, the matter that makes up each galaxy collapsed towards a center. If you will remember from my Big Bang video, Edwin Hubble was the first to discover that there are other galaxies. The object we know as the Andromeda Galaxy was previously known as the Andromeda Nebula. It was known that it was made of a collection of stars and dust, but they couldn't see the true structure or scale of Andromeda with the technology of the time. Only by observing Cepheid variable stars in the Andromeda Galaxy and calculating their apparent magnitude could Hubble and others calculate roughly how far away these galaxies were. Although their early estimates underestimated the distances, they still got numbers that put these nebulae way too far away to be part of the Milky Way. Thus, the scale of the universe as we knew it grew exponentially. But we already covered this. What we are going to do today is cover the different types of galaxies and discuss their properties and structure, and what makes them different. Spiral galaxies are ones which have distinct arms. There can be multiple arms, and there are even major and minor ones, as well as what are called spurs, which stick out of the arms. A galactic arm is a band of stars and space dust. All galaxies rotate, and so the arms of spiral galaxies form as clusters of millions or billions of stars string together in a way. The arms all extend away from the center of the galaxy, where the majority of matter, including stars, is concentrated. That's why spiral galaxies look so much brighter in the center. There are several types of spiral galaxies, the differences between which aren't important, but we will take a look at some examples. Pinwheel galaxies have arms that spiral continuously from the center to the outer edges. Barred galaxies contain a linear band of stars that extend away from the center of the galaxy. This bar eventually develops into spiral arms. It's not really understood how these galaxies develop bars, but we do know that most spiral galaxies have bars. I want to take a moment to point something out here. You'll notice that these galaxies are tilted at various different angles. Space has no true orientation. North, south, east, west, x-axis, y-axis, z-axis, these don't really mean anything in space. Our solar system has its own plane, and our galaxy is much wider than it is thick, but the way other solar systems and galaxies form their own plane is unique and dependent upon local conditions. There is no master plan or preferred plane. The next type of galaxy is called an elliptical galaxy, which get their name from being oval or elliptical in shape. While spiral galaxies have highly distinct bands, ellipticals have nothing of the sort. Like spiral galaxies, most of the stars and matter in ellipticals is concentrated in the center, but from there, the material that makes up the galaxy spreads out uniformly, gradually becoming less and less dense. From what we can tell, elliptical galaxies are all very old, and they are the result of collisions of numerous other galaxies. Spirals, such as the Milky Way, are thought to almost all be the result of dwarf galaxies colliding. Imagine if we took individual blobs of yellow and blue paint and started swirling them. At first you would see bands of yellow and blue, which are distinct. This is like what we see in the structure of spiral galaxies. But eventually, the material mixes enough times that it becomes a uniform green. This is similar to what we see in the structure of elliptical galaxies. Elliptical galaxies are thought to also result from the collision of multiple spiral galaxies. This will eventually happen to Andromeda and Milky Way. They are on a collision course. It won't be for billions of years, so don't worry. But even if it were happening right now, you probably still wouldn't have to worry. When two galaxies collide, the odds of anything large colliding is about 0. Again, on the scale of solar systems, the gaps between objects is massive. Although the galaxies slam into each other at hundreds of kilometers per second, it takes hundreds of millions of years for the galaxies to fully intermix. That's how big galaxies are. While it may look like the stars are bouncing off of each other, they aren't. It's the gravitational fields of the objects that interact and cause objects to change position. While our solar system might get flung into a wildly different place in the cosmos as a result of this collision, the orbits of the planets around the sun are likely to remain stable. We have photographs of spiral galaxies mid-collision, on their way to becoming a single elliptical galaxy. Trillions of years from now, it may be the case that almost all galaxies are elliptical, but for now they aren't. Speaking of collisions, there are peculiar galaxies. Peculiar galaxies have odd morphologies, and we think it's because they are the result of galactic collisions. It's sort of like looking at the debris after a car crash. It's pretty hard to tell exactly how everything got to the point where you see it. In between an elliptical and a spiral galaxy is a lenticular galaxy. I'm just gonna let the photographs show you what distinguishes these galaxies. There are also ring galaxies, such as Hoag's object. Again, I'll let the photographs do the talking. Then finally, there are irregular galaxies. These galaxies simply don't fit into any other classification system and don't share consistent features that we can use to group them. So we group them by the absence of features. Around a quarter of the galaxies we observe are irregulars, and they're almost all much smaller than spiral galaxies like the Milky Way. Our closest galactic neighbors are the Large Magellanic Clouds, which are irregulars. While they are small, they are busy little objects. The Tarantula Nebula, located within one of the clouds, is the fastest forming star region in the local group of galaxies around us. One final similarity between the large elliptical and spiral galaxies. Virtually every one of them has a supermassive black hole in the center, millions to billions of times the mass of the Sun. This appears to be an inevitable part of galactic evolution. Matter is concentrated highest towards the center, so a black hole inevitably forms, and it can collect material from the many millions of stars that are close to it. In the 20th century, astronomers began finding what are called quasars, which is shorthand for quasi-stellar objects, or star-like objects. They're the brightest objects in the universe, but they're not stars. They come from black holes. In some galaxies, the center is so dense that the supermassive black hole in the center is fed with huge amounts of material. As that material spirals towards the black hole, it accelerates to near the speed of light. This creates unimaginable amounts of friction and energy, which propagates outward as light. Enormous bands of radiation, thousands of light years across, blast out from the poles of black holes perpendicular to the disk of rotating material surrounding it. Some of these can be seen from a side view here from Earth. Others are pointed directly at us. The Hubble telescope can see quasars that are billions of light years away, and they appear as bright as some stars in our own Milky Way galaxy. Galaxies that contain quasars are known as active galaxies. We will end this video with one of the most bizarre discoveries ever in astronomy. Let's say we want to figure out the mass of the Sun. How do we do that? It turns out we don't need to know anything about the size or composition of the Sun. We can determine it just based off of Earth's distance from the Sun and the speed at which Earth orbits the Sun. Newton's equations allow us to calculate the Sun's mass based off of this. The speed at which we orbit the Sun directly depends on our distance from it, but also the Sun's mass. If the sun were more massive, we would orbit around it faster. Now, how do you tell how massive a galaxy is? You could try to count every single star in it, but that would be awful. However, we do have estimates of galactic mass based off of what's visible. A much easier way to precisely measure galactic mass is to see how fast the galaxy rotates. The speed of rotation of the galaxy will tell you how much mass it contains, very similar to how we calculate the sun's mass. But there's a catch. It takes the Milky Way 200 million years to rotate 360 degrees. So by looking at a galaxy, you'd never be able to detect any of its motion unless you looked at it for thousands of years. Instead, astronomers look at the Doppler shift of the nebulae at the edge of the galaxy. Remember, the Doppler shift is a shift in the apparent wavelength of light coming from an object as it moves towards or away from us at ludicrously high speeds. If we observe the edge of the galaxy and see how much its light is redshifted, we can calculate how fast it is moving away from us, hence how fast the galaxy is rotating. This is like peeking at the speedometer of a moving car. Most of the early work in this was done by Vera Rubin. When she observed the edges of galaxies and calculated the redshift, there was a big problem. The edges of the galaxies were rotating way too fast. Based on estimations from the amount of visible matter that makes up the galaxies, there's no way the outer edges could be rotating that fast. In fact, some observations showed that in some regions, rotation speeds up as you move away from the center, or the speed of rotation remains constant rather than constantly decreasing as it should. Imagine the blades of a wind turbine. The blades spin in unison because they are one single unit, but the gas and stars that make up galaxies are not. They are only attracted to each other by gravity. Visible matter in these galaxies only accounted for 15% of the gravitational force required to make the edges of the galaxies rotate as fast as they do. The galaxies also rotated so fast that they should fly apart. The strength of gravity from the visible material couldn't possibly hold on to objects rotating that quickly at a distance. Something that could not be detected, did not interact with ordinary matter, did not emit any energy on the electromagnetic spectrum, was present in these galaxies and accounted for the vast majority of the gravitational force within them. That substance is called dark matter, and it will be part of our next video. Thanks for watching.